Hello and welcome to the video channel of the CRC 768. My name is Gennadiy Koltun and I'm working as a research associate at the Institute of Automation and Information Systems at the Technical University of Munich. In the following, I would like to outline the Subproject A6, dealing with model document coupling for lifecycle integrated engineering in mechatronic systems domain. Okay, why is this essential? Let's start with the motivation and an overview on engineering in mechatronic systems domain. Let's take a look at the innovative lifecycle of mechatronic systems. During the whole lifecycle of mechatronic systems, various stakeholders are involved. Within the development phase, for instance, initially requirements and the rough design of a mechatronic systems is derived. Mechanical, electrical, as well as software engineers detail the system's design within their discipline, considering particular aspects. When it comes to commissioning of mechatronic systems, further aspects become relevant. For example, testing and simulation, which can potentially reduce the time to market. Hence, costs can be saved while the quality of the system is raised. Nevertheless, during the operation phase, technicians and maintenance engineers have to maintain the system components. For instance, the average lifetime of mechanical components is 30 to 50 years, while the lifetime of software is significantly shorter. You all have experienced this when working on the computer and getting a notification of a new software update. In summary, mechatronic systems are complex in order to fulfill particular customer requirements and to compete with global market trends. Hence, nowadays mechatronic systems become so-called product service systems. But let's come to the question we address in this project. Why is interdisciplinary collaboration challenging? Implicit dependencies between disciplines exist. This means we have dependencies between stakeholders and processes, models, documents, and computer-aided engineering tools of each discipline, and machine data. As highlighted, in this video we focus on models, documents, and computer-aided engineering tools. Let us make this more concrete at one example. The electrical engineer, which is one of the mechatronic engineers, recurrently designs electrical projects for mechatronic systems. This means the electrical engineer creates models within vendor-specific computer-aided engineering tools. Note that this is done under time pressure. Once he finishes the project, particular aspects of the models are exported. For example, the circuit diagram, a type of engineering document which serves as the basis for technicians and the electrical installation at the customer premises. Unfortunately, ideal and reality differ. For instance, due to weather conditions, the technicians decide to install slightly different components than originally intended, in order to cope with the unexpected weather constraints. Moreover, due to his long experience, he knows further installation steps, which are not specifically captured in the document. Finally, he tracks changes within the circuit diagram. Now the engineering document and the original engineering model differ. In order to avoid inconsistencies, they must be synchronized and adjusted. How is this process of change propagation realized? Initially, the changed circuit diagram is sent to the electrical engineer. Subsequently, the technician has to install the next mechatronic system at the next customer premises. However, note that the electrical engineer has to design the next project. Thus, under pressure, he tries to identify and interpret changes in order to maintain the ECAD model within their computer-aided engineering tool. The success of this procedure alternates significantly depending on the given context. In conclusion, engineering sources are inconsistent and/or incompatible. Possible reasons for this are manifold, but in the end, there is lack of communication between involved stakeholders, and there is a lack of knowledge due to stakeholder-specific knowledge that is not well known to other stakeholders. Consequently, different understanding and actions resulting from it reproduce further discrepancies. In conclusion, engineering sources are inconsistent and incompatible. This can lead to unnecessary cost excesses or project prolongations. Therefore, we target the development of supportive approaches. Note, this is only one example for many. For sure, you will recognize similar cases in your individual environment. To preserve the lifetime information from engineering documents, we propose a model document coupling. Besides the inconsistency management that we also investigate in the CRC 768, I refer to my colleagues from the subproject D1. Model document coupling deals with first the retrieval of information and its analysis, and second, the preservation of distribution of this information across disciplines. Just take into account one change in the engineering document can affect various stakeholders, processes, models, and other documents from other disciplines. In fact, our current focus includes the following 2 points. We identify and classify and formalize relevant stakeholder and discipline-specific knowledge, and based on this, we plan a handbook for the tailored development of systemized and collaborative model document coupling for your individual problem case. Thank you for watching this video. If you have any questions, please consult us via mail. Subscribe to our video channel if you like this video. Bye and see you soon.